This is my development setup for using a PICAXE-18M2 microcontroller. Let me show you. As you can see, we have a blinking LED that's connected to one of the output pins on the PICAXE. This is a DS1307 real-time clock. This is a 10K potentiometer that's tied into one of the pins. Here's another two LEDs that are not being used at the moment. Down here is a Dallas semiconductor centigrade temperature sensor. We will get a look at that and how it's used as well. This is going to be a series of how-to basic programs for the PICAXE. And the first thing we will look at, of course, is why my LED is blinking. There's two ways to blink an LED, and both are very easy. And this will introduce you to some basics on the PICAXE and how to program it and set it up. Shown here are my basic pin connections to the PICAXE-18M2 controller. In reality, this is a microchip controller, PIC. It has 18 pins, has a built-in basic interpreter, and it's been wired up on my development board as follows for these series of videos. First of all, let's note C3 and C4 are really not available. Those are the serial I/O connections that go back to the computer, which I'll discuss a little bit separately. Pin C.5, which is pin 4, is input only. So I pulled it up to high through a 10K resistor and connected a switch off to ground. That is the switch I'll be pressing through most of the videos. So there's my switch to be detected and used for various purposes. Dropping down to B.3, which is pin 8, I've connected an LED through a 1K resistor to ground. Also on pins C.7 and C.6 also have LEDs connected off the ground that will be used for various purposes. On pin 17, there are 18 pins on this device. I have 1 Hertz in. There, remember if you saw the introductory video, there is a DS1307 clock chip, real-time clock, does time, and it has a 1 Hertz pulse out, and it's tied into C.0. Note we have 2 pulse width modulation outputs on this particular device, B.3 and B.6. Also note up here, C.1 will be programmed, several of these pins can be programmed individually as analog to digital converters. In this case, I've tied this off to a 10K resistor. If you build this, make sure you have this bypass cap. It keeps noise off the 5-volt lines. For those of you who are new to schematics, note that this 5 volts, that 5 volts, and that 5 volts are electrically the same connection. Note, they're the same connection for you new people into electronics. This ground here is this ground here, and that ground there are all the same electrical connections. So note that if this is your first time looking at a schematic. Finally, it is very easy to connect I2C devices such as, in this case, a DS1307 real-time clock, and in another demo we will be connecting a chip to expand our I/O ports. B.1 is your serial data. B.4 is your serial clock for your I2C. All right, let's move on. Here's a brief look at the PICAXE serial I/O connections. In the case of my demo board in the earlier video, I use this one down here. You'd have to hook these up, and in all cases You cannot get around it. I've tried and it won't work. You've got to have that 22K and that 10K resistor here. And so you can connect this essentially to this, as long as you keep your pin connections correct. This up here, this is an audio connection, an audio plug. You can buy a USB to adapter that would plug into this particular setup if you want to use this. So I'm using this one down here. You can buy a pre-assembled board, I suppose, from PICAXE. I built my own, as illustrated earlier. So note, that's why you couldn't use these two pins here. Now I'm going to discuss how to program the PICAXE, assuming that you have the serial cable connected correctly and everything electrically is ready to go. You can open up your PICAXE programming editor. In this case, I'm using version 5.5.5. That's the slightly older one. They got a newer version that you can download. I prefer this version here. There is their website if you want to go to it, and so forth. And various copyrights or whatever. The software or firmware within the PICAXE chip is copyrighted. So, and you're probably not going to be able to get it out anyway. But anything that you write based on it is not. So your programs are yours. Anyway, what's the first thing we got to do? Let's open up a file. Go to File, go to Open. And we're just going to do Blink. Just blink an LED. That's what you saw in the introductory video. Let's note how this works to basically set this up. Anything that's a semicolon is a comment. It is not seen by the compiler and ignored. I always put in, and when you boot this thing up from nothing, it will ask you which PICAXE to use, but just in case, I always put in here that this is an 18M2 chip. Now, let's note an interesting thing. The 18M2, you can adjust the clock frequency anywhere from 31 kilohertz to 32 megahertz. I mean, this thing will fly at 32 megahertz. If you, in fact, it defaults to 4 megahertz. So as far as that goes, you don't need that particular command. If you just want to default to 4 megahertz, I would leave it in there just in case you want to change it later on. It defaults to 4 megahertz, or you can, if you're not sure, go ahead and do that. This is our blink LED. All right. Remember when you saw the diagram earlier, you saw that there were pin numbers B.3, B.4, and so forth. You can look at the schematic. This is the blinking LED that was connected to pin 9, which is B.3. Here we have the term symbol. LED equals B.3. Anywhere I use LED, it's going to assume, of course, it's B.3. Now, I could use B.3 and leave this out totally if I want to, but it's better programming to do it this way. So, what did we do? I'm going to set the LED high. That's going to turn it on. I'm going to pause 500 milliseconds. Pause is in milliseconds. Pause is in milliseconds. Oh, if you want to see this a little bit bigger than what it is, come up here to font size and go to 12. And there you are. It's a little bit bigger for you. All right. Another nice little thing. So pause is in milliseconds. Now, if you set this for a different set frequency differently, what if I set the frequency for M8, for 8 megahertz? Pause does not adjust to different clock speeds. Note that right off the bat. If I was to set this for M8 or 8 megahertz, pause is now in units of half milliseconds. So 500 pause, 500 milliseconds is going to become 250 milliseconds or so, I believe. It definitely changes the delays and other stuff. So unless you have good reasons to, and you'll have to, if you're going to use the terminal, if you change the clock speed, you're going to have to watch out about changing certain things in the system. Remember, changing clock speed, you have to change certain things in the system. All right, what do we do now? You have up here syntax. It will check to see if you've written it down correctly and there are no problems. Syntax successful. I use 17 bytes out of 2048. The program memory, at least in the 18M2 part, is 2048 bytes. But you see, the system here breaks it into basically what we call tokens. So blinking this LED only took 17 out of the 2048 bytes. Like I said, this thing defaults to 4 megahertz, so I don't really need to set that. Let's do syntax again. Just by getting rid of a command that I did not need, assuming I want the default 4 megahertz, I saved myself 3 bytes. So note, good programmers don't want to use a lot of memory. Now this isn't like programming an Arduino, which I'm also going to cover similar material on, but just by doing that I saved myself 3 bytes. Okay, so the syntax says it works. Assuming my electrical connections are okay, I'm going to hit program. This little screen comes up, and this shows you that it's uploading it, or downloading it as I call it, and downloading data. And it's done. And assuming you had everything working right, the LED will be blinking. That's all there is to it. Now, it does have a function in here called simulate if you want to use it, and it pops up all these little windows. It shows you the memory and the pins and I/O on the pins. If you see right here, this shows right there where I'm blinking B3. Remember, this is an 18-pin part. This could be handy if you just want to simulate it and see what it's doing without actually hooking up a live chip. I generally don't use this that much. I always, and you can reset it, start over. Sort of neat. Simulate off. Anything else we should know? Okay, you can save your program there, or save as any other Windows-based program is. You can open through that folder. You can print this, assuming that it has a printer set up somewhere. You can print your program. You have a number of options. This is the window that you usually see when the programming editor first comes up. It will ask you for the version of the chip. You can even check the firmware version, because I found out this firmware version, there's 1 or 2 commands in their reference that doesn't work. Nonetheless, here's your serial port. I'm using COM1. I don't use flowcharts. Language, you can choose your language. Various colors to suit your, I just leave it at default. The editor, pretty much all of this stuff I leave at default. And that's my advice. So this is how to operate the PICAXE programming editor to set up to set everything up and to get you going. Thanks for listening. We'll look more at specific programs in the following videos.